we have talked in the past about discontinuities. Now, what we have not talked about is discontinuities with a rational function where the denominator has variables in it. Now, these are terms you need to know in calculus. There are two kinds of discontinuities. There are removable, whoops, I meant to do a highlighter right there, dummy. Removable ones and non-removable ones. Now, I don't want you to worry about the difference at this point. That comes in calculus. The only kind of removable discontinuity there is a point discontinuity. Do you remember from last semester what a point discontinuity is? That's the y values approach the same number, but the graph is undefined there. Right, so there's a hole. So the description of the graph on a point discontinuity, the two pieces of the graph approach the same number. I'm going to do that for approaches. The two pieces of the graph approach the same number. If we look down at this graph right here, that graph has a point discontinuity at x equals 1. Do you notice that the y values are getting closer and closer to the same thing, right? Now, I want you to look right down here. You should be able to tell from that graph what the domain and range of that function are. Is domain x or y? X. So we're going to read left to right, just like we do a book. Negative infinity to where? To 1. Is 1 included in the domain? Nope. And 1 to infinity. Good. So all real numbers except 1. What's the range? The same. Why do we have to leave out y equals 1? Why? Yeah, because there's another piece. Yeah. So, right, y equal 1 is not included there, but is included there. To infinity. Good. Good catch, Isaiah. You're welcome. All right, an infinite discontinuity. An infinite discontinuity has a vertical asymptote in it. So the description of the graph, the two pieces of the graph approach positive or negative infinity because the graph has a vertical asymptote. So if we look down at this picture, this graph has a discontinuity at x equals 1. It is a removable, it's a non-removable discontinuity because it's a vertical asymptote. Again, don't worry about removable and non-removable at this point. Do you see that as the x values are getting closer and closer to 1 from this direction, what are the y values doing? Approaching infinity, right? And as x approaches 1 from this direction, what are the y values doing? Right. And the only time your graph's going to approach plus or minus infinity is when you have a vertical asymptote. Now, you can get a slant asymptote too, but we're not worried about slants at this moment. Let's talk about the domain and range of this function. What's the domain? Look at that. They have, this one and that first one have the same domain. But this one has a vertical asymptote and that one has a hole. Okay. What's the range? Yeah. All real numbers. There's nothing left out. So far, so good. Last graph. The last one is a jump discontinuity. Do you remember a jump? A jump discontinuity is when the y values approach two completely different numbers. So, description. The two pieces of the graph approach different numbers. So let's look at this picture. A jump discontinuity is non-removable. This one's got a jump discontinuity at x equal 1 because when we get to x equal 1, we have to jump up here to keep graphing. What's the domain? Really? What about x equal 1? Oh, but it's defined here. Good. So all real numbers. Now, did you notice on the point discontinuity, that x value was left out? On the vertical asymptote, that x value was left out. On this particular jump discontinuity, that point was not left out, was it? Because it was defined on one of the pieces. What's the range? All real numbers. Good, good. Because this y value is covered right there. Let me show you in a nutshell what a removable discontinuity is. A point discontinuity is the only one that can be removable. Why? Because if I make one point in one place, that thing's continuous. If I fill in that hole, that function's continuous, isn't it? I'd never have to lift my pencil. That's a removable discontinuity. And that's as much as you need to know right now. Next page. See, we got through that page fast. Okay. We've got what, 4 of these? We ain't doing 4 of them. We'll probably do, I'll do 2 with you, and then I'll have you do 1, and then we'll move on to the last page. Okay. Now the first thing we're going to do is just revisit Algebra 2 just a little bit. Now please don't have, you know, a stroke or anything about revisiting Algebra 2. I want to remind you of the connection between the function itself and the graph, because I'm doing this in my Algebra 2 class right now. Do you remember how you find vertical asymptotes? That's horizontal asymptotes. Horizontal asymptotes come from comparing the degrees. Whatever makes the denominator 0. Now there's one hitch to that. Do you remember how to find a hole?
Whatever cancels, like whenever you factor it.
That's right. Any factors that factor out of the numerator and denominator create your hole. And anything that's left in the denominator will create your vertical asymptote. Let's factor. Factor that numerator. Now I got a 2x squared, so where's my 2 go? 2x and x? Yeah, sure. 2x and x? Help me out here. All right. Indeed. I couldn't read it, though. You'd have to teach me. The language I know is math. Um, I am multilingual, bilingual. I know English and math. How do you factor the denominator? I wish I was bilingual, for sure. I wish I was. What do you see here? When you factor out a common factor out of the top and bottom, what does that mean to you? It means there's a whole. And how do you know where the whole is? That's right. It's whatever makes that 0. What makes x minus 3 equal to 0? X equal 3. So that's why I've got a whole at x equal 3. Now, notice what I've got left. How do I find the y value of the whole? Now, degrees give me a horizontal asymptote. How do I find the y value of that whole? That's right. I plug that x value of 3 into what I've got left. So if I plug in a 3 there, I've got 7 over 5. That's where that comes from. Yes? Okay. How do you get a horizontal? Yeah. How do you get a horizontal asymptote? Compare the degrees. What's the degree of the top? 2. What's the degree of the bottom? 2. So if the degrees are the same, the coefficients, 2 divided by 1, 2. So y equal 2 is your horizontal asymptote. How do you find your vertical asymptote? Whatever I have left in the denominator. What makes that 0? X equal negative 2. That's why I have a vertical asymptote at x equal negative 2. Is that ringing bells? I just wanted to make sure you remembered where everything came from. Does that make better sense?
Yes.
Okay. Now, all we're going to do is fill in these blanks, and we're just going to do it by looking at the graph. As x approaches negative infinity, that means the x values are going this way. This says the graph of f of x approaches what? And that means the y values approach what? As x gets smaller, follow the graph. As x gets smaller, what are the y values doing? They're approaching 2, right? You see that they're approaching 2? They're approaching that horizontal asymptote. As x approaches infinity, the y values also are approaching 2. Oh, now we'll talk about that in a minute. As x approaches 3 from the left, so here's x equal 3, right? From the left means from numbers smaller than 3. So we're coming at it this way. As x gets closer and closer to 3, what are the y values getting closer and closer to? 7/5. 7/5. As x approaches 3 from the right, so look where x is going. What are the y values getting closer and closer to? 7/5 again. Let me show you some notation. You will use this notation in calculus. Let me do this. This piece right here, as x approaches 3 from the left, we write it in calculus like this. X approaches 3 from the left. When you see this little negative or positive sign up high after the number, x approaches 3 from the left, and that means from numbers smaller than 3. If we want from the right, we'll just make that plus. That says as x approaches 3 from the right, which means from numbers bigger than 3. So we don't have to write all these words. Mathematicians are lazy writers. We write it like that. I'm sorry, that is math language. Yes, and it's beautiful. Mathematics is the language with which God wrote the universe, according to Galileo. He was pretty smart, so. Okay. He's pretty smart. Okay, as x approaches -2 from the left, here's x equal -2. X is getting closer and closer to -2 from that side. Yep. Indeed, as x approaches -2 from the right. Okay, let's try that again. What's the domain? Yes? What got left out? The whole and the, which one? Vertical asymptote got left out. What's the range? -infinity to 7/5, 7/5 to 2, and 2 to infinity. What got left out? The y value of the whole and the horizontal asymptote. Does the y value of the whole always get left out? You betcha. Would the y value of the whole had gotten left out of the range there? Nope. Nope. All right. Let's try this one. We're not going to go and factor and see where everything came from. Let's just go. This tells you what the coordinates of the whole are. As x approaches -infinity, what do the y values get closer to? 1. You holler if there's something that you're like, I don't know how you got that number. As x approaches infinity, what do the y values get closer to? 1. Stop right there. What is y equals 1? The horizontal asymptote. Ladies and gentlemen, the definition of a horizontal asymptote is, what does the graph do as x approaches positive or negative infinity? That's what a horizontal asymptote is. Did you have, if you had Mrs. Siegert, I'm sure you did you have any graphs that ever crossed the horizontal asymptote and you were like, it can't do that? No? Yeah. Yeah. Did, if you ever had like 2 vertical asymptotes and 1 horizontal asymptote, and right here in the middle, it crossed the horizontal asymptote. This is where this gets explained. A horizontal asymptote is not what happens at 2 or 3 or 1 or 0. Horizontal asymptotes are what happens on the ends. I don't give a hoo-ha what happens in close. I want to know what happens way out here and way out here. That's why it's okay to cross a horizontal asymptote, because it's not crossing way out on the ends. This is the definition of a horizontal asymptote. What happens as that function approach, excuse me, as the x values approach positive and negative infinity. You never learned that before, did you? Okay. As x approaches -3 from the left, 1/2, I agree. 1/2. Right there. Remember a point discontinuity? The two pieces of your graph are approaching the same y value, but there's a hole there. So same value, x is approaching the same value, but one from the left and one from the right. That's a point discontinuity. As x approaches 1 from the left, 1 from the left, yeah, negative infinity. As x approaches 1 from the right, infinity. What kind of discontinuity is a vertical asymptote called? Look back at your front page if you can't remember. An infinite discontinuity, and I hope that makes sense because the graph is approaching infinity or negative infinity. That's why it's called an infinite discontinuity. Domain and range. What's the domain of this thing? Okay. What got left out? Why did -3 get left out? Because it's the whole. It's the x value of the whole. Why did 1 get left out? The x value of the, be specific, vertical asymptote. What's your range? Not only can I not talk fast, I can't write fast either. Why did y equal 1/2 get left out? Good, the y value of the whole. Why did y equal 1 get left out? The horizontal asymptote. You okay so far? Guys, what you have done here, these are what we call in calculus limits. The whole first unit of calculus is on limits. The foundation, the basement, the building block of calculus is the idea of a limit. All right. So see, you're already learning a little calculus. Heck yeah. Heck yeah. Now, I want you guys to go to the second one on the next page, and I want you to do it. When you get some answers, talk to people around you and see if you're getting the same thing. You got some answers? As x approaches negative infinity? 2? Positive infinity? What do we find when we approach positive and negative infinity? The horizontal asymptote, right. As x approaches -2 from the left, -1, because we can only be here, right? As x approaches -2 from the right, what kind of discontinuity do we have there? For that particular piece, we have a point discontinuity. Because as x approaches -2 from both sides, the y values approach the same number. That's a point discontinuity. As x approaches -3 from the left, when, as x approaches -3 from both sides, we go to positive or negative infinity, what did we just find? Vertical asymptote. Question. Does one have to go positive infinity and the other have to go negative infinity? Could they both go the same way? Could they? If they wanted to? No, it's not a parabola. Question. Where are the horizontal asymptotes?
It's 0.
Horizontal asymptotes, you compare the degrees, right? What's the degree of the top? 0. What's the degree of the bottom? 2. Biggest exponent is 2. Degree of the top is smaller than the bottom. So y equals 0. So I have horizontal asymptote right here. What's your vertical asymptote? X equals 0 because that's where the denominator is 0. If I put negative numbers in there and I square them, what am I going to get? Positive numbers. If I put positive numbers in there and square them, what am I going to get? This graph looks like this. Looks like a volcano. What I'm saying to you is when you have a vertical asymptote, both sides can approach positive infinity, or both sides can approach negative infinity, or they can do one of each. Doesn't matter. All of those mean vertical asymptote. Domain and range. What you got on domain? Okay, whoa, slow. Start again. Negative infinity to negative 3. Wait. Go ahead. Negative infinity to negative 1. Yeah, that's it. Last page. Now what the last page is, at least for the top half, is just a summary. What have we just figured out? I've already talked you through it. Based on your observations from what we just did, fill in the blanks or answer the question. If the graph of f of x as x, if the graph of f of x approaches a, that means the y values approach some number as x approaches infinity or negative infinity. So as x approaches infinity or negative infinity, and the y values are getting closer and closer to some number, what do we find? Horizontal asymptote. Yep. If the graph approaches some number b, as x approaches some number a. So as x is approaching some number, both the y values are approaching the same number. Now I'm going to write this. I have a potential point discontinuity, meaning I have a potential hole. Discontinuity. Why do I say potential? Is that crooked? Look at this. As x is approaching, let's just call that 2. As x approaches 2 from the left and from the right, my y value is approaching that. But I don't have a discontinuity there, do I? But the y values are approaching the same number, aren't they? So just because the y values approach the same number, the hole, there may not be a hole. There may be, but it may be filled in, and there's not a hole at all, and this thing's continuous. That's why there might be a point discontinuity, because the hole might be filled in. Right. If the graph approaches infinity or negative infinity, as x approaches some number, now x is not going to the ends, as x approaches some number, and the y values approach infinity or negative infinity, You got a vertical asymptote, right? Almost done. Shoot. We're going to be finished by 5 after.
Yay!
How do you determine the domain of the rational functions that we've done so far? What got left out? Domain. Which one? Which got left out of the domain? Vertical or horizontal asymptotes? Vertical. What else got left out? The x value of the whole. Right. So the domain is all real numbers except the x value of wholes or vertical asymptotes. That's what's going to get left out. How did we determine the range? What gets left out of range? All right. So somebody's got the hiccups. All real numbers except the y value of wholes. Now, does the y value of a whole always get left out? No. So let's do this. Potentially. You got to be careful on that one. But the horizontal asymptote's always going to get left out. And the horizontal asymptote. Now, the AP Calculus exam is real big on you being able to read a table. So let's just talk about this. We just got, what, 1, 2, 4 questions left? The table shows selected values on the graph of some rational function f of x. Use the information in the table to answer the questions. Now, you see that this row is the x values, and this row is the y values, right? Where do we have problems? Yeah, why do we have problems when x equals -½ or 2? Because the y value is undefined. Wait a minute. What causes an undefined y value? Of what kind of asymptote? Horizontal asymptote or a vertical asymptote? I'm an idiot. I mean, yeah, a horizontal asymptote, and I'm waving my hand up and down. A vertical asymptote or a whole. Good. Well, which one? Let's look at -½ And I want you to look at the y values around here. We can determine from the y values what's happening. Why do you think asymptote? Okay. Yeah. Take a look right here. As x is getting closer and closer to -½ look at the y values. Look, that number, this thing nosedives, doesn't it? What's it do from this side as x is getting closer to -½ from the right? It goes from 1.6 to 251. So it's going like that, right? So what does that tell us? We got a dang VA, right? We got a vertical asymptote. I think we just answered question B. Yes? We have a vertical asymptote. What's the equation of the vertical asymptote? X equals negative 0.5. Why? Because the function approaches look right here. If the function approaches infinity or negative infinity as x approaches some number. As x approaches this number, do the y values approach infinity or negative infinity? Heck yeah, that's a vertical asymptote. So give a reason. As x approaches, now I'm going to show you some nice little notation. Okay, do that. F of x approaches negative infinity, and as x approaches negative a half from the right, f of x approaches infinity. And that's the definition of a horizontal, of a vertical asymptote. I want to go back to this one. Let's talk about what happens when x is 2. As x approaches 2 from the left and from the right, what do you see the y values doing? What number are the y values getting closer and closer to? Do you see? Look at, read it in 1.2. Okay. You see these numbers are real close together, aren't they? And it would make sense that there would be a hole at the point 2, 1.6. Because the y values are approaching the same number as x approaches 2 from the left and the right. So the coordinates of the hole, what are the coordinates of the hole? Give a reason. As x approaches 2 from both sides, f of x approaches 1.6. Remember I showed you this notation? As x approaches 2 from the right and as x approaches 2 from the left. Somebody yesterday said, well, can't I do this? No. No. Can't do that. That's not recognized mathematics notation. That's not in my vocabulary. Okay. Yeah, I can't argue it, but no. Huh?
Can it be slang? Math slang?
Can it be math slang? It can be math slang as long as you're not talking to a math professor about it, because they'd have an absolute fit. You start developing bad habits now, and then you take a math class in college, and they'll say, what math teacher let you do that? And you say, oh, this Stinnett over at Siloam. And I would be, my name would be Mud. A. Identify the equation of any horizontal asymptote. How do you determine a horizontal asymptote? If the graph approaches some number as x approaches infinity or negative infinity. So we're going on the ends. I want you to look at and as x is going this way and as x is going this way, what do you see about the y value? What are your y values doing as x is getting farther and farther to the ends? Well, the x's are. What are the y's doing? They're approaching 1.5, aren't they? Do you see those x values are getting closer to 1.5?
Yeah. Oh.
On both ends. Same number on both ends. But the deal is, now you're thinking, well, why is it bigger than 1.5 on the right end and smaller than 1.5 on the left end? Yeah, it's because of that horizontal asymptote. This one is going to come at it from the top, and this one's going to come at it from the bottom. So horizontal asymptote is HA, y equals or x equals? Y equals. Give a reason for your answer. You have a horizontal asymptote when? F as x approaches. Now you can do this, plus or minus infinity. F of x approaches 1.5. Now let me show you how we're going to write that in calculus. In calculus, we're going to write this. It's LIM for limit. So this is what you will see in calculus. So again, mathematicians are lazy writers. When we get to calculus, we won't write out all this. We'll write this. And you read it as the limit of f of x as x approaches infinity is 1.5. Okay. Yeah, if you want to. Well, okay, then if you're going to do it, you're going to do it right. So this one, the limit of f of x as x approaches, I don't remember the number, -1/2. As x approaches -1/2. Now, do you see that did different things from the left and from the right? Went to negative infinity from the left and went to positive infinity from the right. You see what I'm saying there? So what we would have to say is, as x approaches -1.5 or 0.5 from the left is negative infinity, and the limit of f of x as x approaches -0.5 from the right is positive infinity. I remember learning how to do that and feeling really smart, thinking I was like some big hotshot because I understood that. Domain and range, and we'll be done. Can you find the domain from this table? Negative infinity to -0.5. Is that included? Is that included? That's your domain. What's your range? Is Maribel the only one who knows anything right here? Y'all are good with that? You're good, Maribel? All right. Go ahead. Okay, let's sometimes on the vertical, I need a little picture. Where did we have issues? We had issues when x was -0.5, and we had issues when x was 2, right? We had a vertical asymptote there. Well, that's fat. I didn't mean to do that. Had a vertical asymptote there and had a hole there. That's helpful to me to do the whatever it's called. Oh, and we had a horizontal asymptote right there, didn't we? Because this y value is, what's that y value? 1.6. What 1.6? And this y value was 1.5. Now can you do the range? negative infinity to 1.5. Ooh, and 1.5 to 1.6. There you go. That is very hard for me to do off the graph. I need to draw a little picture. Okay. Now, you know what a limit is. So when you start calculus, juniors, and when you start calculus, if you need it in college, no?